Cool. Well, thank you very much for the kind introduction, Gareth, and I'm very, very pleased to be here. So yeah, I'm Brendan Maginnis. I'm the CEO of Sorcery, and I founded Sorcery because I love refactoring code. And like any good programmer, I eventually got to the stage where I wanted to automate the process. So that's what Sorcery is all about. It automatically refactors code as you're writing it. And it really acts like a pair programmer that's sat beside you, reading the code as you write it, understanding it, and then just tapping you on the shoulder and saying, hey, here's a little improvement you can make. And then you make the improvement to your code and you carry on going. So that's not what I'm here to talk about today. Today, we're going to talk about functional programming. And we're going to take about how we can take existing Python code and refactor it so it's written in the functional programming style. And I'm going to demonstrate this with a live coding example where I take an existing implementation of noughts and crosses and refactor it into the functional programming style. And this will show us what functional code looks like in Python programs, how we can introduce it into an existing program, and then we'll talk about some of the benefits. So before we do any of that, Gareth, will you play me at noughts and crosses?
All right. We'll give it a shot. Go easy on me here.
Okay. So I will go first. So I pick a square from 1 to 9. So let's go with 2.
Okay, so I think I will go for the middle one. So that must be number 5, right?
5. Okay. I will go with 1.
That must mean I have to stop you at 3.
Ooh, blocked. Okay. So I will go for 7. Ah, typo.
So that makes my life a lot easier. So that I will go for 7 then. Thank you very much.
Well played. Okay, so I really need some undo functionality in this. Right, let's play one more time. Let's see how we get on second time round. First to 2. Okay, you can go first.
So I'll go for the middle one. So I think 5. I'm a happy person in the middle.
Okay, I will go for 8.
So therefore, I will go for number 9.
Okay, I better stop you in 1.
And I will go for 3.
Ah, you forked me.
And then I make it so I go then for 6, right?
6. Ah, lovely. Okay, you win. Okay. What I'd really like to do is watch a replay of that because you absolutely thrashed me. So we've got some new requirements for this game. We want to be able to undo the last move, and let's say by typing U, or we can show a replay of the whole game by typing R. So let's check out the code. So this is what we've got. There's a main function. This is the main logic. So it says input a square from 1 to 9, creates a new game, and while the game is not finished, we read the next move, apply the move, and display the game, and keep going until the game is finished, and then finally we display the results. So that's nice and simple. And then we've got a player class for X and O, which is a string enum, and then we've got this noughts and crosses code. Okay, so it's storing the turn, who's playing next, and it's storing the position as a list of either nuns or player X or O. And then when we play a move, we update the position and we swap the turn. And then we've got a couple of check functions. So is the game finished? If there's a winner, then there is, or if all of the squares are occupied, then the game is finished. And then we have the winner code. So this checks if all of the columns or rows or diagonals are all of the same type. So all player X or player O. And if there is, there's a winner. We return that winner. And then finally, we've got the display code. So this prints out the position, and then we print out the result. So let's think about this. Let's jump in and add the undo functionality straight away. How can we do this? Well, we could, when we call the move function, we could just store the last position, and we could store a list of all of the moves. Yeah, let's store a list of all the moves. And then we can just add an undo method to noughts and crosses. So whenever the player types U, then we call undo, and then we undo the last move. We turn the position into what it was before. And then for a replay, we can just create a new noughts and crosses object, play through the moves again, display the position. So that all sounds good. So shall we get started? Whoa there, stop. This is not what we want to do. Whenever we make a change to code, it's always a good opportunity to refactor. So it's always better to refactor first before adding new features. Then it's easier to add the new functionality. So in case you don't know, refactoring is the process of restructuring existing code without changing its external behavior. So once we've refactored noughts and crosses, it's going to have exactly the same functionality, but it's going to be easier to extend to add the undo and the replay functionality. So in this case, we're going to refactor it into the functional programming star. So we're going to talk about two aspects of functional programming, pure functions and immutable data. So a pure function has two properties. It's referentially transparent. So that means if we pass in the same arguments, then we get the same result. So it can't depend on non-local variables that change. We can't have any mutable reference arguments. So for example, if we pass in a list to the length function, then if we pass in an empty list, then length will return 0. But if we then append to that list, then the length will have 1. So that's an example where the list is a mutable reference argument. And another example is self. In this case, in noughts and crosses, when we call the move method, we're updating the self. We're updating self. And so that's why when we call the display function, it will give a different output each time. And then the other thing that we can't do is read from input streams. So in this case, we're reading from the command line, but it could also be reading from the database or reading from the network. And then the other property is no side effects. So we can't update non-local variables, mutable reference arguments, or input-output streams. So it's similar. Instead of reading, it's more about writing from these things. And so an important aspect about pure functions is if we call another impure function, then the calling code is automatically impure too. So it's tainted. Once something is impure, if anything else calls it, it's also impure. So we have to build out pure functions on top of pure functions. So let me give you a summary of what a pure function is. Do not read or write mutable state or the outside world, and do not call impure functions. So then the other aspects we're going to talk about is immutable data structures. So this just says data cannot be changed after it has been created. So in the noughts and crosses case, we wouldn't be allowed to call the move method that updates the state. And if we have immutable data structures, it makes it much easier to create pure functions. And we'll see that soon. So let's look at the code to see some examples. So input, that's not referentially transparent because we call it with the same argument and it gives us a different result. In this case, we're typing in 1 to 9, it's giving us a different result each time. The int function, this is a pure function. It only depends on what we pass into it. So that's very nice. Move. So it updates the result of it updates the state of noughts and crosses. So this cannot be a pure function. And additionally, it's also printing out. So it's writing to an output stream. And then we've got display and display result. So both of these print out. So again, they're writing to an output stream and are not pure. Okay, let's look at winner. So this looks pretty good. It's the only thing it's depending on is, well, it only depends on its arguments. It doesn't write any state, but there is a problem. It depends on self.position, and self.position is mutated in the move method. So we can call winner on the same object and we get different results. And then the final thing to note is noughts and crosses is not an immutable data structure because we've got this move method that's updating the state. So if we've got all this input, printing and updating state, how can we turn this into functional code? So, hold on. I would like to introduce the functional core imperative shell pattern. So the way this works is all the domain logic, all of the business logic of your code, it lives in the functional core, and we only use pure functions and immutable data structures. And then surrounding that is a very thin imperative shell that handles all the interaction with the outside world and contains mutable values. So it prints to the command line, it reads the input, maybe it writes to the database, and it could contain changing state as well. And so the important aspect is the imperative shell depends on the functional core, but not vice versa. And that's because of that aspect of if something calls something impure, then it automatically becomes impure. So that's why we have this diagram of the imperative shell wrapping the functional core. So how do we achieve this with existing code? We start from the inside and we go outwards. We start with the domain logic in the core of the program, and then we make it functional. And then we push any imperative code outside of that. And then we keep going layer by layer until there's a really clean split between the functional core and the imperative shell. And you'll know you'll have achieved this when all the domain logic lives in modules which have no side effects or mutable state. And all imperative code lives in other modules which call this functional core domain logic. So let's get back to noughts and crosses. What are we going to aim for? We're going to turn the noughts and crosses class into an immutable data structure and turn all of its methods into pure functions. And then we're going to move all of the printing and mutable state into the main function. Simple. So it's live coding time. So one thing I always like to do when I'm writing Python code is include type information. And type information always makes it much easier when we're refactoring code. So the main function doesn't return anything, so its result type is none. And when we ever have code where the result type is none, it's a very strong indicator that the code is impure. And in this case, it's quite clear. It's calling print and it's displaying results and it's reading information. So if we go to noughts and crosses, init methods always return none. And let's set the turn to player, and the position is a list of optional players. So I just need to import this. So the square's an int and it returns none. Okay, so that's another indicator that this is an impure function. So finished looks as though it returns true or false. And winner returns either the player or none. So it's an optional player. And display, again, returns none. So this is impure. And display result also returns none. So that's impure too. So all of these methods that are returning none in noughts and crosses, there's a clear sign to us that these are impure. And we can see that because they're calling print in all cases. So let's have a look. Let's refactor this code. So first thing to do is, let's see what this is. Okay, I've got Sorcery installed. It's giving me a refactoring suggestion. How convenient. So let's have a look. The function can be refactored with the following changes. I have an English description, and then at the bottom, I can see the code change. So that's quite simple. I'm going to apply it, and that looks quite clear. I can actually make this even simpler. So it's either winner or all the positions. And winner is actually an optional player, but we should be returning a bool. So let's just wrap that in bool. So that code is nice and clear and simple. And here's another sorcery suggestion. Okay, let's apply that. Great. So now let's move on to these imperative methods. So let's start with display result. So this one's quite simple. What we're going to do is we're going to return a string, and then in the main code, we're going to print that string. So let's turn that to string. And we're getting a warning from MyPy, which is telling us that this is not returning a string. So if we just turn this into return, nice. And then where we were displaying the result, we can just print it. And actually, this is no longer displaying the result, so let's rename the function as well. Okay. So let's try display. This is the same sort of thing. We're going to return a string, and we're going to have to accumulate the result here. So we'll start with an empty string. We're going to add each result. And then finally, we're going to return the result. Okay, so Sorcery has picked up another refactoring. So let's have a look at this. Okay, that looks a lot simpler using an if expression. So I'll apply that. And then because this is a string enum, the position is a string enum, then I can actually remove this value. And then actually Sorcery is offering me another suggestion. So let's apply that. That becomes simpler still. And let's inline this. And then actually, because one of the things that we've achieved by removing the print statement is now we're working only with strings. And so we can use all of the string functionality and string functions that come with Python. So in this case, we can actually use string.join. So let's do that. Oops. Okay, suddenly this code is starting to get much clearer. Okay, so there's something going on. We haven't actually printed this yet, so let's print it. And actually, printing display, well, actually we're printing the game state. And in this case, the game state is really the representation of what the game is. So instead of calling game.display, let's rename this to dunder string. So when we call print game, it's actually calling this string method. So let's just test things out to see if it's still working. Okay, excellent. Right then, now it's on to the big one. We've got the move method, and this is the one which does all sorts of things. It's printing and it's updating state. So firstly, let's get rid of the print. Okay, so the way that we're going to get rid of this is we're actually going to raise an exception instead and say this square is already occupied. And then in this game code, we're going to check for that. And we're going to print it. And actually, we need to declare this duplicate. Move exception. Okay, so that's the first step. But then the more challenging step is, well, if we can't update the state.
Brendan?
Hello?
So, hi, Brendan. I think you dropped out there a few seconds. So if you wouldn't mind going a little bit back in your talk, I think there was a dropout on our end. So you were just about to change the move state. So if you can go back maybe 10 seconds in your talk, that would be great.
Yeah, okay. So is this the right spot?
Yes, that's good. Thanks.
Okay, so
sorry.
that's all right. Yes, so the move is going to print out the square, but we need to remove that if we're going to make it pure. So instead, what we're going to do is raise an exception to say this position has already been moved, and then we're going to print that. We're going to catch that exception, and we're going to print it in the main game loop. So if we raise an exception and capture it here. And the other thing we need to do is, of course, declare that exception. Okay, so that's the easy bit. Then the difficult bit is if we can't update the state of noughts and crosses, how can we possibly make this move method work? So there's a trick that happens all the time in functional programming, which is that we, instead of updating the state, we return a new version of noughts and crosses. So let's start by saying that we're going to return a new noughts and crosses instance. And actually, we're going to have to pass in the new turn and the new position. So the new turn is quite simply this, what was previously updated with the turn, and the new position is slightly more complicated. We'll take the existing position and copy it, and then update the position for that. And then the problem is that noughts and crosses doesn't take a new turn and new position, but we can quickly set that up. And we're going to add default arguments so that if we don't pass anything in, it still sets it up as it was previously. Actually, let's call these turn and position. Okay, so let's test this. there's something wrong. Okay, we've called move, and now we're returning a new noughts and crosses. But here, it's not doing anything. We actually need to update this existing game. So let's just set that like this. Okay, excellent, excellent. So we've reached this ideal. We've got the functional core. We've got the noughts and crosses code. It's completely immutable data. We never update the data, and all of the methods are pure functions. And then wrapping around that is this imperative shell, where all of the input and output code exists, and all the mutable state exists. So now it's much, much easier to extend. So let's add that undo functionality that we were talking about. So how are we going to do that? Well, quite a simple thing we could do is just store the history of all the moves. So there's the starting move, and whenever a new move is taken, we just add it. And then we want to undo. So if the action is, oops, let's drop the last move and then replace the game with the previous position. So let's try that out. Play some moves, and then I can undo them. Okay, if I undo the first move, there's causes an error. So let's just check that the history is greater than 1, so that if we undo at the start, it doesn't do anything. Okay, excellent. And then final thing to do is add replay. So this is going to be really easy as well. Let's ask if we want to show a replay. And if the user says yes, then for old position in history, let's print the old, and let's just sleep for 1 second between each of those. Okay. So, Gareth, let's play again. Winner takes all. Winner takes all.
Challenge accepted. Very good. So are you playing first or am I playing first?
You can play first.
So I'm going to go for 5.
Okay, I'll go for 1.
I would like to go for 2.
2. Okay, I'm going to block you at 8.
And then I go for 3.
Okay, I'm going to block you again.
And then I go for 6. No, I can't. 9. I have to block you, right? I have to block you, right?
Oh, you've left the gap.
Yes. I had to let you.
Now let's watch this. Where was the mistake? That's the question. I'm not quite sure. Well, let's call it a draw overall. Let's call it a draw. Well nice. Played. Well played.
Sweet.
Okay, so what are the benefits of this functional programming style? So the big one is testing. Because pure functions only depend on their parameters and have no side effects, it's extremely easy to test. We just pass in some values and check the output. Think about the display and string methods on noughts and crosses. Previously, they were printing, which is always very messy to test. Whereas now they return a string, and so we can just check that the right string is being output. And then even the winner and the finish methods are much easier to test now, because we can create a new noughts and crosses class in any position because the noughts and crosses init method now takes a turn and a position. So we can set that up and test those very, very simply. So the second advantage is reusable code. So we've already seen right there how easy it was to repurpose functional code, in this case to add undo and replay. But also let's think about the display and string methods again. Previously, they were always printing to the command line, but now we could save that output in a file, we could send it over the network, we could do whatever we like with it. We've separated out the printing from the actual logic, and so it's much easier to reuse. And then the final benefit is functional code is simple to understand. The great thing is it's just very, very easy to reason about. We only need to consider the arguments to a pure function to work out what the output will be. There's no chance that another part of the program will change the state under our feet. And so there's a limited surface area to read to work out exactly what's going on. So, in summary, functional programming, we've got pure functions, which are referentially transparent and have no side effects. And we build them around immutable data structures. Once created, they never change. Secondly, always refactor your code before you add new functionality because it makes everything easier. And then finally, use Sorcery to help you refactor. Thank you very much.
Very good, very good. So Brendan, there are a few questions that came through that I'd like to take the opportunity to ask you. So one of the questions that came through is someone mentioned that this is, even though it sounds like a very simple example of noughts and crosses, it illustrates a common thing that people push for time, they code things, and then they get it working. But then the question is this refactoring. It seems like it's always a burden to refactor. And the question is, in your experience, do people really go back and refactor enough? And what are some best practices that maybe organizations can adopt to kind of create an environment where refactoring is a good thing? So you showed it in a simple example. The code started off being hard to explain, and then you made changes and it become a bit easier, and at a certain point, nice and easy to read, and also made your life easier to change things. In your experience, what are some good practices companies should adopt in teams to kind of get this philosophy going?
I think the first thing is to start with your own code. Make it first a practice for yourself. So whenever you're writing code, think, actually, I'm probably going to spend the same amount of time writing this if I first refactor it into a good structure, and then I can add the functionality. And so over time, as you build up this muscle, this refactoring muscle, you become better at it, and you start to build up some evidence that this is the case. People will start working with the code that you've worked on and go, oh, this looks really nice. How has this happened? And then you can say to people, well, I always refactor my code. I make sure it's very nice. Then I add the functionality. And so building like a groundswell of opinion within your team is often a good way to go. Talk about refactoring, do it a lot. If you're pair programming, always refactor with your pair and get it going. And then once you have a group of people who are with you on that, then it's something that you can take upwards and say, look, I think we should actually do this as a regular practice. There should be some time allocated to refactoring as well as just the time that we spend when we're writing code. Right.
No, that's good. That's good. So thank you for that. And then the next question that kind of came up is, it seemed that in a simple example, and I'm sure you don't do this always, you kind of are testing manually, so you're hacking your testing, right? So hacking is maybe a strong word, but you were testing as you go, right? Do you have any thoughts on should there be more unit testing? Would it have been a nicer addition, or did you on purpose not show unit testing because you wanted to prove functional programming as opposed to how to better test code?
Yeah, I mean, I fully recommend getting your code under test before refactoring. So as you can see, I had to go back a couple of times to fix mistakes that I had made, and the testing would have found that out. So firstly, the type information helps you identify some of the errors that you introduce when refactoring, but tests are much more powerful at doing this. So in the sorcery code base, we refactor the functional core of sorcery mercilessly. We're constantly refactoring and making it better. But we have very, very high test coverage of that functional core. And so we can make very aggressive changes to the code base because we know we're covered. And we know whenever we make those changes, if we make any mistakes, then they'll be spotted by our tests. So yeah, I actually recommend writing the test first, then refactoring, and then adding the functionality.
Very good. And then there's another question that kind of came through is, so you're the founder of Sorcery, right? So this is a very powerful tool. It seemed like you used it seamlessly in your workflow. Can you maybe tell us a little bit more about what's behind? Is there some secret magic sauce behind this? And how should we use it? So is this only something for Visual Studio Code, or can you tell us a little bit more about it? Because it sounds like a pretty useful tool for everyone to kind of learn as they go along, the same way you did it.
Yes. So can you see me? I was just switching off the presentation. Yeah, absolutely. So it's available for PyCharm and VS Code. That's what we fully support. And then there's also integrations for Vim, which I was using just now, Sublime, and Emacs actually, although I've never actually tested that. So I hope that it works. That was a user contributed integration. Yeah, so the other place that it actually works is we have a command line interface that allows it to be integrated into a CI pipeline. And we also have a GitHub bot that reviews pull requests and suggests refactorings on any other changes that have been made. But yeah, actually the integration in VS Code and PyCharm is a lot smoother and cleaner than the one that we saw in Vim there, and has some additional functionality like being able to scan a whole folder to find all of the refactorings there, or scan for duplicate code across part of your code base. So yeah, I really recommend just downloading Sorcery, checking that out and seeing how it works, and send me an email with any feedback that you have. I'd love to hear it.
Nice. So while you were talking, one last question came through, and then we'll while you're answering this question, I'll ask the next group of people. So that will be Sako and Dorian to get ready. So the question came from Deepak. He said, object-oriented and functional programming are two paradigms. Having knowledge of both of them is really good. In a simple example as this, I actually found the original object-oriented approach may be more readable. But just to be sure, functional programming is really beneficial. Do you have, based on your experience, some examples where you would just say, go with functional programming as something that people could look into?
I mean, from my experience, whenever I've adopted this approach, it has benefits on larger scale programs. So especially if you're not so used to functional programming, then it can be a bit confusing. And like you say, maybe in this example, the code is slightly simpler to understand, at least in the initial version of the code before you add undo and replay. If you're adding undo and replay with the imperative style, it would be really quite messy to get that right. And so we, even in this small case, we can see some benefits of the functional style. In terms of an example of where this is really, really powerful that we've used is in the Sorcery code base, the refactoring engine is almost entirely functional, and it's 15,000 lines of code. And there's a huge number of tests of that. And if there was, having it split out like that, with something, well, the thing about Sorcery is it has to be correct. We can't ever break your code. And so having something that's really reliable is very, very important. And the way that we've structured the code in this functional style allows us to test it from end to end very easily with any of the different inputs, any different type of code that we need. And we found it to be extremely reliable. Sorcery tends to have almost no bugs in the core engine, and all the bugs that we tend to find are in the imperative wrappers that are around the edge. So the integration into VS Code or PyCharm or the GitHub bot, that's where we find the bugs are. So in my experience, it works very, very well, but it does take some practice to get used to this style of writing code, definitely.